Have you ever gazed up at the night sky and wondered what it would be like to just jump? Not from a plane, but from space itself. What would happen if you took a leap of faith from the edge of our atmosphere? Would you burn up, explode, or would you gently float down like a feather? Well, today we're going on an imaginary journey to find out. Strap in, because this is going to be one wild ride. First things first, let's define space. For this thought experiment, we'll start our jump from the Kármán line, which is about 100 kilometers or 62 miles above sea level. This is the internationally recognized boundary where Earth's atmosphere ends and outer space begins. Up here, the air is so thin, it's practically a vacuum. So, what's the very first thing that happens when you step off your hypothetical space platform? You wouldn't immediately plummet. Instead, you'd start to float, still in orbit around the Earth. To actually fall towards the planet, you'd need to cancel out your orbital velocity. Satellites and the International Space Station are moving at incredible speeds, about 17,500 miles per hour, to stay in orbit. If you just stepped off, you'd be moving at that same speed. So, let us assume you have a futuristic rocket pack that you use to slow yourself down to a near standstill relative to the Earth. Now, you're truly falling. For the first part of your descent, it would be eerily quiet and peaceful. Without any significant atmosphere, there's no air resistance, no sound, no wind rushing past you. You'd just be in a state of free fall, accelerating due to Earth's gravity. You'd see the magnificent curve of our planet below, a breathtaking panorama of blue oceans, swirling white clouds, and continents of green and brown. It would be a silent, beautiful, and utterly terrifying experience. But this silent phase won't last long. As you fall deeper, you start to encounter the upper layers of our atmosphere, the thermosphere, then the mesosphere. The air particles, though still sparse, are there, and you're hitting them at an incredible speed. This is where things get heated, literally. The friction between your body and the air molecules would start to generate an immense amount of heat. This is the same principle that causes meteors to burn up and glow as shooting stars. To survive this, you can't just be in your regular clothes. You'd need a highly advanced spacesuit, something far beyond what astronauts wear for spacewalks. This suit would need a robust heat shield, similar to what space capsules use for re-entry. It would have to withstand temperatures potentially reaching thousands of degrees Fahrenheit. Without it, you'd be incinerated in moments. This suit would also need to be pressurized. The lack of atmospheric pressure in the upper atmosphere would cause the fluids in your body, like your blood and the water in your tissues, to boil, a gruesome process called ebullition. So, a pressurized heat-resistant suit is non-negotiable. As you continue to fall, hurtling through the mesosphere and into the stratosphere, the air gets thicker. Air resistance starts to become a major factor. Your acceleration will slow down as the drag force increases. Eventually, you'll reach a point where the upward force of air resistance equals the downward force of gravity. This is called terminal velocity. But what would your terminal velocity be? For a skydiver in a typical belly-to-earth position, terminal velocity is around 120 miles per hour. But you're falling from much higher, and you're entering the atmosphere at hypersonic speeds. Your initial terminal velocity in the thin upper atmosphere would be incredibly high, much faster than the speed of sound. This would create a sonic boom, a thunderous clap that would echo for miles, announcing your arrival. You would be a human meteorite. Your specialized suit would need to handle these extreme forces. The rapid deceleration and the shockwaves would be brutal. The suit would need an internal stabilization system to stop you from tumbling uncontrollably, which could be disorienting and dangerous. Think of it like a sophisticated combination of a spacecraft's re-entry system and a skydiver's wingsuit, all packed into one person-sized package. After surviving the fiery re-entry and the hypersonic speeds, you'd be descending through the stratosphere and then the troposphere, the layer of the atmosphere where we live and where weather happens. By now, your speed would have slowed down considerably, likely to a more conventional terminal velocity of around 120 to 200 miles per hour, depending on your body position and the suit's design. The view would have changed dramatically. The blackness of space would be replaced by the deep blue sky. You'd see clouds, not just below you, but all around you. You might even fall through one, experiencing a sudden, damp chill. The silent fall would be over. Now, you'd hear the deafening roar of the wind rushing past you, a constant, powerful reminder of your speed. But you're still falling way too fast to land safely. The final, and arguably most crucial part of your journey is the landing. Hitting the ground at 120 miles per hour would be just as fatal as burning up on re-entry. So, your incredible suit needs one more feature: a parachute system, and not just one. You'd need a multi-stage parachute deployment. At a safe altitude, maybe around 10,000 to 15,000 feet, you deploy a small drogue parachute first. This is designed to work at high speeds to slow you down and stabilize your descent further. Deploying a large main parachute immediately could rip it to shreds or cause a dangerously abrupt deceleration. After the drogue chute has done its job and slowed you down to a manageable speed, you would then deploy your main parachute. With the main canopy open, your descent would slow dramatically to a much safer speed, perhaps around 15 miles per hour. The roaring wind would subside into a gentle whoosh. For the first time in this entire journey, you might actually be able to relax for a moment and enjoy the view. You'd float gently towards the ground, a tiny speck returning from the cosmos. And then, touchdown. You'd land on Earth, hopefully in a soft open field and not in the middle of an ocean or a busy city. You'd unbuckle your helmet, take your first breath of fresh terrestrial air, and feel the solid ground beneath your feet. The entire journey, from jumping off the Kármán line to landing, would probably take around 10 to 15 minutes, depending on the specifics of your trajectory and equipment. This incredible feat was actually accomplished in a way by Felix Baumgartner in 2012 and later by Alan Eustace in 2014. Baumgartner jumped from an altitude of about 24 miles and Eustace from over 25 miles, both in the stratosphere, not technically space. They both broke the sound barrier in their descent and relied on pressurized suits and parachutes to survive. Their jumps gave us real-world data on what it is like to fall from the edge of space. So, what happens if you jump from space? You don't just fall. You re-enter the atmosphere like a spacecraft, endure extreme heat and G-forces, break the sound barrier, and then, if everything goes perfectly, you deploy a series of parachutes to land safely back on Earth. It's a journey that pushes the limits of human endurance and technology. It's a transition from the silent void to the roaring winds of our own world. A beautiful, violent, and ultimately life-affirming fall from the stars. What a mind-blowing concept, right? It really makes you appreciate the complex physics and engineering that protect our astronauts and the incredible life-sustaining blanket that is our atmosphere. Thanks for joining me on this cosmic dive. If you enjoyed this journey, don't forget to hit that like button and subscribe for more adventures into the what-ifs of science. Until next time, keep looking up.